So in this problem, we're going to draw a shear and a moment diagram. Right, what we're interested in finding are internal forces. So ultimately, we have a pretty good idea that that's going to end up using the blue saw at X. And if we had the internal forces, then we would also be able to calculate the state of stress. Right? And in the problem statement, it tells you that this is an indeterminate beam and you're supposed to use superposition. And we're even going to use the roller at the right end as the redundant force. But let's unwind for just a moment here. How do we know it's indeterminate? Let's look over at the wall. The wall would have three external supports. Two perpendicular forces for translational restraint, and also a moment for the rotational restraint. Over at the right end, we've got a roller, which gives us one external unknown. So that's going to be a total of 4 external unknowns. And we only have one free body diagram. We have a beam that goes from the wall to the roller. So we have 3 equations, giving us a 1-degree indeterminate structure. Now this happens to be indeterminate in the transverse direction. Right? We only have one red arrow, which would be in the axial direction from the wall. So this is indeterminate in the transverse direction. So to use superposition, we are going to need to define a redundant force. So what we're going to do is use the roller force as the redundant force, as it says right there. So how do we set up our superposition? We've got the actual beam, right? Always remembering that the actual is going to be equal to the sum of its structures. So we've got the actual beam, right? Wall and a roller. And now we take the roller restraint, the kinematic restraint, away. We remove it. And now we have a determinate cantilevered beam, 5 meters. Right, that's one we can solve using statics, or we're going to help ourselves out by using a deflection table. Structure 2 down here is going to be the exact same determinate structure, but sitting on it is the redundant force. I've just happened to call it F10. So before we can unlock this superposition scheme, we need to solve for F10. Right? That's the extra equation that we need. And so this can only be true, right, if we make sure that the kinematic that is true in the actual structure is held true in structures 1 and 2 when we add them together. So that would mean that the actual displacement at 5 meters, which is equal to 0, is going to have to be equal to the deflection in structure 1 at 5 plus the deflection in structure 2 at 5. Right, this is the first thing that we have to do here. It's going to give us the answer for F10 when we do it. And then once we have F10 solved for, we can use superposition to add these quantities together in structure 1 and 2. So there's our approach. We've got a deflection table here. And so we need some deflection. So let's look over here in structure 2. We've got a cantilever with a point load at the end. So that's going to be case 1. Right? We're going to be interested in using the max deflection, which happens to be at the location of the point load. So we're going to end up using PL cubed over 3EI here in just a minute. Let's take a look at structure 1. Right now, structure 1 is a cantilever that has 2 applied moments on it. So what we're going to do is take structure 1 and break it up into 2 pieces. I will call them structure 1A and 1B. And if we do that, structure 1 now breaks down to a simple cantilever with a single applied moment at 3 meters, and also the moment that's sitting out there, again, the applied moment that's out there at 5 meters. So what we need are the deflections out at the free end here. So I need V1 at 5 meters. Let's take a look at the deflected shape before we dissect that equation. So the deflected shape is going to look like a curve, right? Coming away from a point that is restrained with translation and rotation. And then beyond the application of the point moment, we're going to have a straight line. And if we look out on these last 2 meters, inside the beam, the moment's equal to 0, which means we have no curvature. So that part of the beam is just along for the ride. So to find the total deflection out at the end, we're going to use geometry and superposition. So we're going to find the deflection at 3, right, which is where the moment is applied. We're going to then add to it the slope at 3 and multiply by those 2 meters. In structure 1B now, the deflection out at 5 is going to be a little easier to solve for. Right? We're going to use, let's go back up to see what we got here. We have some needs here. We're going to need the deflection and also the slope that occurs at the location of the point load. So let's go up here and grab these numbers. The deflection is right there. It's going to be an ml squared over 2EI. Again, remember that L is the distance from the wall to the applied moment, not the length of the beam. In this case, it is, because the moment's applied all the way out at the end of the beam. And here would be the slope at the end, which would be ml over EI. So let's go ahead and apply those. We're going to add the deflection at 5 and 1A plus 1B plus V2, structure 2, deflection at 5. So the deflection in 1A is made up of 2 pieces. There's our 2, there would be the deflection at 3, there would be the slope at 3, and there would be multiplied by 2 meters, so there's our geometry. So that right there would be just the first term in total. So if I just slide right back up here, that is this right there, those 2 pieces. So there's our superposition determinant. All right, V1B, the deflection at 5 and 1B, is going to be ml squared over 2EI. And the deflection in structure 2 at 5 is going to be PL cubed over 3EI. And so P is F10. Right? Length is 5 meters over 3EI. So there's the equation. All it is simple math from there. We just multiply it out. EI's all cancel. And we go ahead and solve for F10. We end up getting a negative number, which means that back here in the picture where I drew it, right there, a negative number would just mean that it is it's actually pointed in the other direction. So this is what we just did to our free body diagram. Right? We solved for the reaction in the roller. And so now we can go ahead and solve for the other 3 unknowns over here. We have 3 unknowns. And we have not yet used any equations of equilibrium on this. So we would have 3 equations left. So statics now will be enough. We used superposition, which dealt with the deformation of the member, and so we can, right, that counts as our constitution equation. So F1, F2, and M1 by statics. So I'll let you solve on that. Be good one to do on your own. And what that does is create a solved free body diagram. And so from this, we're going to draw the shear and the moment. And so the shear diagram is pretty straightforward. As we move left to right across the beam, we encounter a point load going up. So that bumps us up 0.24 kilonewtons. The only thing that's going to move the shear diagram is an applied load, right? Not an applied moment, but an applied point load or distributed load. There are no loads on the beam. And so we then encounter at the end a point load going down. And so that becomes our shear diagram. There's a relationship between shear and moment. And so let me see if we can work our way across this here. As we get onto the beam, we encounter a moment that would be counterclockwise. That's going to kick us down on the moment diagram to 1.2 to minus 1.2. And the area underneath the shear diagram over the next 3 meters is going to be 0.24 times 3, which gives us 0.72. So the change in the moment diagram between or over the next 3 meters is going to be minus 1.2 plus 0.72, ending with a moment of minus 0.48. Right there on the beam, we encounter now an applied moment. And think of yourself as moving left to right, and this thing is spinning. That would cause you to get kicked up if this were spinning. So that bumps us up right here, a value 5. So ending up at plus 4.52, and then the change in the moment diagram is going to be plus 0.48 over the next 2 meters. That gets us all the way to 5. And we do have closure because at the end we have the applied moment. And so that's going to kick us down. So we end up getting closure on our moment diagram. You're also asked to find the slope at the end, or the rotation at the roller. So let's just go right back to our superposition. Right, we've got these 3 structures, right? A structure 1A, a structure 1B, and a structure 2. And so I'm just about to run out of room, but structure 2 no longer has F1 as red, but it has a known value on it. So if I wanted to find the slope over here in the actual member, right, in my actual beam, all I'm going to do is take the answer in the 3 beams below. So the slope here would be ML over EI, noticing that the slope is going to be positive. So I've got positive. Right, the slope at 5 meters in structure 1B, right, the slope out here at 5 is going to be the same as the slope at 3 because we've got no moment. So we've got plus partial V partial X at 5 meters is equal to M L, L being 3, which is the distance from the wall to the moment, over EI. And then the very last one, we would have the PL squared over 2EI, which would be back in the table. All we're going to do is add those numbers all together by math. And we are now home free. We get a positive number. And positive would relate to angle with a counterclockwise rotation.